we're finishing up inequalities. And the last sort of inequality that we're going to do the last types of inequalities that we're going to do are those involving polynomials or rational functions. This is section 2. Inequalities involving polynomials or rational functions.
And our exam will go to this.
No. Exam goes to the material on Monday. Monday's the not today. Today is Wednesday.
Isn't our exam on Monday?
Yes.
Oh, so what we did on Monday, right?
Yes. Not next Monday. Yeah.
Yeah,
Last
I
Monday.
said.
That's why you were so confused. So, yeah, I once had a, not forget. Okay, so polynomials. You guys know what polynomials are, right?
Yeah.
Rational functions. Do you all know what rational functions are? Anyone not know what rational functions? Rational, just think of rational numbers, right? Rational, in that case, meant a ratio, right? A ratio of numbers. Remember, the rational numbers look like this, a ratio of integers, right? A ratio of integers. Rational functions is the same sort of thing. You have a ratio, right? A ratio of polynomials. You've got two polynomials, P and Q polynomials. Right? These guys, right? So anything like x squared plus x plus 1, 5 plus 4 plus 3 squared. Right? Polynomial on top of another polynomial. Right? You see that these things are undefined wherever the denominator has a root, right? And then they reach 0 where the numerator has a root. Right? They're going to be 0 where the, well, actually, just be careful. That's pretty true. Wherever the numerator has the root, as long as we're not at the place where the denominator is undefined, where the denominator is 0. So first off, it's undefined wherever the denominator is 0. And then you look at the places where it is defined, and wherever it is defined, if the numerator is 0, then it has a root. Anyway, rational functions. We'll do the polynomials first. Okay. So here's the example. You have a polynomial. Let's say 9 times x minus 4 times x squared x minus 4. And you put in an equality, and in an inequality, okay, right? You want to know where is this polynomial less than 0? Okay. So we ask first, where is it 0? Okay, where is it 0? And can anyone tell me just by looking at it, like right now, where the zeros are? Lauren.
X equals 4 and x equals -3.
And
positive 3.
great. Very good. Right. So x equals 4. Maybe Lauren in your head factor it out, distribute it out to 9 minus x squared. Right. Distribute it out to 9 minus x squared, or distribute out the x minus 4, however you want to think about it. And said, okay, well, I got this 3 minus x, 3 plus x here. And I've got an x minus 4. Okay, so my zeros are at Okay, so the first thing you ask is, where are the zeros? So here we're looking at the graph of this thing. We know that 3 minus 3 and 4, the function crosses the x-axis, right? And we make this following observation, that between the zeros, the sign of the polynomial cannot change. Okay. That is, like between here and here, we can't have it sometimes positive and sometimes negative. Like it can't be like sometimes positive here and sometimes negative here, between the zeros. Okay. Why not? Why not? I'm going to ban you guys from speaking. It's good. Should be like, I did that. Why not? Why not? Why couldn't this happen? Why couldn't, we've got these two zeros here, these are the only zeros, right? These are the only zeros, and we're saying that the polynomial can't be, between two successive zeros, it can't be positive and then negative. Both of this k.
That's where they go up and down.
Because what?
That's where they go up and down and cross over at the x-axis.
So if it did that, it would cross the x-axis again. There would be another zero. There should be another zero there, right? But there is no zero. Okay. So why not? Because by the continuity of the polynomial, it would then have to have another zero, which it doesn't, right? And so this is using this thing called the continuity of continuity of polynomials. And really, to be honest, we can't explain this to you. We can't explain this to you properly yet. So if you take the next course, if you take calculus, say, that will explain continuities. But to be honest, in that course, we still don't explain continuity to you yet. We give you a sense of it, but we don't really explain it in proper detail. Okay, but so continuity. What does continuity mean to you guys? Have you seen this term before? Continuity, like a function is continuous. Like how has it been described to you?
I usually think that in terms of graphs, like the sine graph is continuous, the graph of the cosine is continuous, and that it doesn't end, it just follows the same pattern.
Okay, so you're saying that here's like the sine and cosine, say, right?
Yeah.
And it's continuous. What is? Because it keeps on going, or you mean it doesn't stop or something? It doesn't have a break in it?
Yeah. It doesn't have a break,
Okay.
it's just an individual graph.
Yeah, so I think at this point in the game, people usually describe it as you can put your pencil on it, and then you can follow it, and you don't put your pencil on or something like that. Right? This is sort of the naive definition of continuity. There's some fancy definition of continuity, but I'm not gonna tell you because it would take. I could explain it to you, but it would take only two lectures to do it, and it's not worth it at this point. In any case, the point is that so really what we're using here is something called the intermediate value theorem. Okay, the intermediate value theorem. Okay, so that is if you're above 0 and you're below 0 and your function is continuous, then it must pass through 0. It will take on that intermediate value. Okay, so if you're curious, look on the internet or in your calculus book for the intermediate value. Okay, So, okay. So the sign of the polynomial can't change between zeros, so all we need to do is check the sign of the polynomial. Let's call this like P of x. Okay? All we need to do is check the sign of the polynomial in each, so it's between zeros. Okay, so in each interval. So here we've got a bunch. Our zeros have broken up the line into four pieces. Right? We've got this piece. We've got this piece. We've got this piece. Oops. We've got this piece. And we've got this piece. And we've got these four intervals, and we know that the sign doesn't change on each of these intervals, and so all we need to do is check the sign in each piece, right? And so we say, well, look, for a gigantic negative number, we're going to get a negative number times a negative number, and so it's positive here. Right? You guys see that? So, right? Let's take like negative a million, say. We look at this thing and ask, is it positive or negative? Where x is equal to negative a million. Right? So, take, say, x to be negative a million. Okay. Then P of x is, right, this 9 minus negative a million squared, right, times negative a million minus 4, right? So you have 9 minus a gigantic number, right, times, so there's a negative number here, we get a negative number and a negative number, so we get a positive number, right? This is bigger than 0. Right? So we check at one point, we find that it's a positive number, so you know everything over here is positive, right? Everything over here is positive. Did people get that? Anyone confused?
Can you just explain that?
Sure. Let me do a simpler one first, actually. Okay, so let's say I'm going to check between negative 3 and 3. Okay, so the rule is that between the zeros, the sign doesn't change. So the sign of every point is the same. Right? It's either going to be all positive or all negative. So all we have to do is check one point. Right? We can check one point. Right? Right? So the easiest point is probably, let's take 0. Okay? We take 0, we plug it in to here, and we get 3 times negative 4. Right? Well, that's negative. Right? So at 0, we know it's negative, and so we know all the way here it's negative. Okay? Right. Same thing for here. I just need to check at one point. So I take x to be a gigantic negative number. Okay. 3 minus a gigantic negative number is positive, right? Because you're subtracting a gigantic negative number. So I get positive. 3 plus a gigantic negative number is negative. The gigantic negative number minus 4 is still negative. So I get positive times a negative, so it's positive. Yeah, Bethany.
So we're not checking to see if it switches, we're just checking to see if it's positive or negative and assuming that it doesn't switch?
Right. So we know it doesn't switch by the continuity.
Okay, so we're not checking it out.
No.
Okay, all right, now I get it.
Yeah. No, we know it doesn't switch, and so we only need to check it at one point. We know it doesn't switch, although we don't really know it. We know it by citing something that you'll get to next term. Yeah, Lauren.
So when we're given the original problem,
Yeah.
the instructions aren't to find the value of x, right? It's to actually graph it. Is
No,
that-
no, no, no. So I'm just sort of sketching out a graph here, but the question at this point is just, for what x is this thing negative?
Okay.
Okay.
Oh, and then you'll be able to tell from the graph which, okay, got it.
So right here, it's positive here, it's negative here. Right. If you take a if you take a number between 3 and 4, what happens? So you're going to get negative, positive, negative, right? 3 minus x is going to be negative because the number is bigger than 3. 3 plus x is going to be positive. So we get negative, positive, and then 3. The number minus 4 is going to be negative, so we get a positive number here. Right? And then out here, gigantic positive number, you see you get all positives, so it's going to be positive. Okay. Okay. And anyone confused by this? If you understand just one case, that's it. All the other cases are the same. And if you understand one move, all the other moves are exactly the same. Right? You take the zeros, you take the zeros, and then you check a point in the intervals bounded by those zeros. Okay. And you see, is it positive or negative? And then you know that in that entire interval, it's positive or negative. That allows you to answer the question, where is the polynomial negative? Right? Where is the polynomial negative? Well, just look at it. Between negative 3 and 3.
Wait, is it the, shouldn't the very last from 4 to infinity be negative? Because it can't be if it goes.
Oh, you're right. I'm sorry. Yeah, sorry. Yeah, sorry, my mistake. So the gigantic, if you take a big positive number, 3 minus the positive number is negative, right? And this is positive, and this is positive. Sorry. Here. So the answer is then between 3 and negative 3, and between 4 and infinity. Thank you. So where is this true? Well, for x 4, negative 3, 3, and 4 infinity. Okay. And the only difference between doing this for polynomials and doing this for rationals is that you need to throw in zeros of the top and the bottom. So for rational functions, the only difference is that for rational functions, it's rather between zeros of either top and bottom. Okay, so if somebody gives you this rational function, you need to figure out the roots of top and bottom, and then you'll get, you get some roots for the top, you get some roots for the bottom, right? And then you just use those intervals. But it's the same game, and for the same reason. The rational function is continuous between these particular points. But it's no more difficult, no more easy or no more difficult than this. So today we're going to chapter 3. We're going to finish chapter 3, which is about functions. And this is something that you've probably already seen, but in any case, we're going to reintroduce it. It may be slightly different from what you've seen before. I'll let you put down a definition. You've got A and B, which are non-empty sets. So this sets of objects could be be numbers, could be things, could be whatever. So a function from A to B is simply a rule associating to each element of A one and only one element of B. So it's a rule associating to, for every element in A, you associate one and only one element of B. So it doesn't like associate two elements of B to it. It doesn't associate sometimes one, you know, it associates in a well-defined manner, you know, this other guy to this element. Okay, and the standard notation is like this. You've got some function f, a, arrow b, taking a to f. Okay, this is sort of like the long-handed form of how one writes functions. And just the way you read this is f is a function from a to b, taking a to f of a. In English. And as you probably know already, the thing that you go from is called the domain, and the thing that you go into is called the range. Okay. So, for example, to give a few examples, we could say if we're going from the real numbers but excluding 2, this slash means excise or exclude. So the real numbers, but except for 2, into R, and it takes x to 1 over x plus 2. And this is sort of like the long, like I said, this is sort of the long way of writing this. So f is the function taking x to x over 2, to 1 over x over 2, right? It has domain this and range that. Right? And normally, you know, people just write something like this, right? Like f of x equals 1 over x plus 2. Abbreviated. People write this, and you just assume that the domain is as large as possible. Right? So you just look at it and you say, well, what x does this make sense for? Right? What x does this make sense for? Well, it makes sense for all x except for 2, so that will be our domain. Sometimes you may see something like this, a colon and then an equal sign, meaning f is defined to be, well, okay, that's also defined to be. Right, another simple example, f of x defined to be the square root of x, right? In that case, what's the domain? What's the domain in this case? If we're talking about real numbers? All positive numbers, or to be strict, all non-negative numbers. So the domain is all real numbers greater than or equal to 0, right? And then the range, what's the range? What's the range?
All, that's what comes out of it. So it's then all real numbers
that people are usually, everyone for some reason is, okay, let me wait until you finish. And then give you the warning. The warning is that everybody's sort of sloppy with this notion of range, okay? Range just means the set that you map into. So it's just as valid to say that the range is the real numbers in this case, because what you get out of it is real numbers, right? Although what Alex said is actually more precisely true, right? What comes out of it is not all real numbers, but rather the non-negative real numbers, right? Okay. So range is sort of an imprecise term. It simply means the set that your outputs land in. Okay. The more precise term for what Alex gave you is the image. Okay. So the image is actually the collection of outputs. Collection of outputs of a function. Okay. And it will lie, of course, inside the range. You could take that as the range. It would make sense to call this thing the range, right? Because it's everything that comes out of the function. Right? So the range is sort of a dislikable term. It's precise. Yeah. So
What's the difference between the?
So range is imprecise. It just means the set that the outputs land in. The set that the outputs land in. The image is actually the outputs. Okay, so for example, for the square root function, the image is all non-negative numbers, because that's really what we get out of it, right? But the range, we could say that the range is the real numbers, even though that includes things that we don't even get. Okay, so for example, like the range of your final grades, right, would be like this. This would be like the range of, if you have a function from this class to the range of final grades. Right? But if this were the image, then that would be sort of disappointing. Does that make sense? If this were the image, that would mean that all of these.
Oh, so it's the difference between what it could be and what it is.
Not almost, because it could include things that it could not be at all, right? Like the negative numbers, it's not going to be negative. Anyway, I think you probably get it. So, okay. Okay. So functions. Equations and functions. And I often abbreviate function just like that. Often an equation determines a function. So for example, to give a very simple example, y equals 3x minus 2. You notice that y is a function of x in the sense that to each value of x, we have associated with it one and only one value for y. I'm going to use this funny looking one to mean one and only one. Later we may see the word if, meaning if and only if. I'm not making this up. Okay, right. Y, for each value of x, right, then you get some value of y, right, in a consistent way. It doesn't there's no choice involved, right? Right, to make it clear that this is a function, the thing is that y, right, y depends on x, right? No, sorry. To make it clear that this is a function, people often write it like this, right? Y of x, right? Y is a function of x. This function. People write it like this. But you could just as well suppress that. So we often suppress it. And just like y equals x2. And I think you know, we call this x the y the dependent variable and x the independent variable. Notice that this function, we could take it in the opposite way, right? We could take it in the opposite way and think of x as a function of y, right? It's just as it's equally valid to say that for this equation, right? We get y plus 2 over 3 equals x, right? X is a function of y also. It depends on how you want to look at it. Which one you want to consider as your dependent, which one you want to consider as independent. Okay. The standard warning, right? Equations will always determine functions. Right? If I have y squared is equal to x, then right, is y a function of x? Is y a function of x in this case? No, so they're shaking your head. Why?
Because to get y on its own, you would have to take the square root of x, and that leaves plus or minus the square root of x, which means that there are two solutions for every y.
Right,
which means
right.
by definition it's not a function.
Right. So there's not a well-defined way, basically. Right? There's not for each value of x, well, there are two possibilities. There are often two possibilities for y. Right? If x is 1, y could be plus 1 or minus 1. Right? If x is 4, y could be plus or minus 2. Right? And so it's not well defined what y could be. Right? And so this doesn't give you right? Y could be either of those things, right? And so you've got two possibilities. You're not associating one and only one value. You've associated one value, but not only one. You've got another one. What about the other way around? Is x a function of y? Is it? John is nodding. Lauren is shaking. Okay, who says yes? X is a function of y? Yes? Who says no? X is not a function of y? Okay, think about it. Right? If you give a value of y, to every value of y, do you get a well-defined value for x? If somebody gives you a value of y, -1, do you know what your x is? One. Yes, you do, right? Right. Somebody gives you a value for y, 1, say, then you know what your x is. 1. Right? X, right? For every value of y, there's a well-defined value for x. Right? Even though it wasn't true the other way around. Right? So like, right? Going the other way, if I say x is 1, what is my y? Alice, what is my y? If x is 1, what is y?
1.
No, it's wrong. I was thinking of -1. right? It's like you could be either one, right?
Yeah.
You could be either one. But this the other way, and I can't play that game. Right? If I say y is 1, what is x? Y is 1, then what is x?
1.
Yeah, I'll shoot, you know, I can't trick you. Right?
Oh,
So
I see. So because they're not equal to each other, they can't be defined. Because they won't give each other the same value.
Well, it's a matter of well-definedness, right? Like, if you know what x is, you don't know what y is. Right? Y could be one of two things. If you know what y is, on the other hand, you definitely know what x is. Right?
So x is
X is a function of y.
but y is not a function of x.
Yes.
Oh, okay.
So it's basically, can somebody play games with you or not? Right? Do you know what the association is? And one way you do, and the other way the rule is not clear. Right? The function is a rule associating to some input, some output. So this one, one way the rule is not clear. Right? No, the rule is not well defined. The other way, yes, the rule is well defined. Okay, does that make sense? You've got these equations, and sometimes you get functions out of them, and sometimes you don't. Any questions about that? Okay. Okay. So, getting back to this thing about range and image, that's kind of a definition of image. So you got the function from A to B. The image, I don't know what they use, I've forgotten what they use in the book, but I think they use range. But let's use image for this because this is what normally people call image. The image of that is the collection of all FAs, the collection of all outputs. Right? The collection of all outputs of the function as A ranges over the domain. Lauren.
So is image just another word for range?
It's a more precise notion than range. So,
Okay.
yeah, it's not the same. It's not the same. Just go back to that f of x being the square root of x. One can say that the range is all of R. Okay. Or you could say that you could say it's all of R greater than or equal to 0. And that's actually more precise. The thing is that the range is simply the thing that you map into. Okay. Yeah.
So A given, is that a big A?
That's a big A. The same big A is here.
Oh, okay.
Sorry, it's more curly. It's the same.
Okay, so it's
So it's just a collection of outputs, right? In English, collection of outputs. Okay. So let me give an example. Suppose you have a function like this. Okay, let's start with something simple. F of x is 2x. What's the image? Let's make it a little, let's start with something simple. So, f of x is 2x, and the domain is this. What's the image? Somebody just tell me, what is it? What's the image? What kind of things do you get out of this kind? Who's this? Tiffany? All real numbers, right? You can get anything out of this, right? Right? The image is all of R. Right? Whereas if I want to get 1 out of this, I just put in 1/2 of 1. If I want to get 2 out of this, I can put in 1/2 of 2, etc., etc. If I want to get 1/2, if I want to get -1 out of this, I put in -1/2. if I want to get y out of this, I put in half of 1, right? Half of 1. Right? To get any value 1, just put in 1 half. Right? You could put, take as the input 1 half. Right. Okay. Okay. F of x, here's a tricky one. F of x is equal to 1 minus x over x. Okay. What's the image? What's the image? What can you get out of this guy?
All real numbers that aren't
All real numbers that aren't
zero.
zero.
That's wrong.
How do you know it's wrong? Did you read my face?
No, it's not.
Okay, let me ask this. Can we get 2 out of this? Can we get y out of this? For y is something? What's the image? I'll let you think about it for... Carol?
I don't think you can get 2 of it because.
Okay. Are you thinking? Are people thinking or just looking? Think. Think or talk to something. Maybe I should say.
This is literally the one.
But yeah.
I'm like, here's why.
Because it would have to be factored to the numerator, and it would always be divided by
Yeah.
Okay, can you get your order? Let's ask. Okay, so right, is there x such that f of x equals 2? Right, that is 1 minus x equals 2. Right? Is there a solution to that? That is 1 minus x equals 3x. Right? In other words, x is equal to 3x. In other words, x will have to be x being 1/3. Right? If we put in 1/3 there, we get 1 minus 1/3 over 1/3. Right? That's say 2/3 over 1/3. That's 2.
Oh, we were wrong.
Right?
Don't worry, it's it.
Okay. Right. You can get 2 out of it. Right? Okay. So 2 is in the image. 2 is in the image. What about 3? Is 3 in the image? You could check if 3 was in the image. You could check if all sorts of numbers are in the image. But this is not the way to find the image, right? Because then you would use up your entire life, checking every number. Right? So let's check it for a general x, a general y. So case of 2. Case of the general number y. Right? Is there x such that f of x equals 1? Right? In other words, 1 minus x over x equals y. Take a minute, no, not even a minute, take 30 seconds or so, and figure out what x would have to be. different other thing. You want to do it? Just do it on the board, right? What do we need to do? Multiply by x, see?
Multiply x,
Right?
add x to side.
Okay. X plus y.
And then you kick back out x. Or you want the right side?
Okay. X is 1 plus y. X times 1 plus 1.
And then you have that quantity.
Right. So that tells you that in order to get y out of this guy, we need to feed it 1 over 1 plus y. Right? Right. So yes, take x to be 1 over 1 plus y, and you see what y we cannot get. What y can't we get? Well, if y is -1, so we can't get y equals -1, but we can get everybody else. Right? For any other number, just take x to be 1 over 1 plus y, and we'll get y. Yes?
So would the answer be all real numbers where y doesn't equal -1?
That's right. That's right. So that would be the image, right? The image is all y such that y is equal to -1.
Do we have to use that notation,
No.
or can we use like human terms, like
Human terms.
real numbers except except -1? You
Yes.
know, like not math people like Rich. Is that okay?
Yeah. Is this human language? Not really? Okay. You can use English. I don't mind. I speak English.
Just checking.
It's faster sometimes to use math notation. Okay. I don't have time to tell you the funny story of how a student, when I first started teaching, a student dropped in class because apparently my accent was too strong. Okay. Okay, another example. I have a lot of funny stories that I sort of repeat from year to year. This will be a good time to talk. I also have a vampire story. A spy story. Here's another example. Okay. What's the image? What's the image? Right. Given an arbitrary y, can we figure out what can we get it? Right? Can we get it as an output? Let's do this one together since we don't have too much time. Right? So let's take an arbitrary line. Okay. And let's see, can we get is there x such that f of x equals 1. Okay. So what do we need to do? It's not all that different. What do we do? Anybody? Multiply. Right. So x plus 2 would have to be y x minus 3. Right. Then? Distribute? Well, we'll move the x over as we did last time. 2 is equal to, we'll subtract x from both sides now. Get xy minus 3y.
Why x1? Oh, so
That's the y-x. I just rid of this x1. And then the y times minus 3, or this minus 3y. we add 3y with the signs. 2 plus 3y equals, why don't you factor the x out of this one? X times minus 1 plus 1. Divide it, we get x would have to be 2 plus 3y over minus 1 plus 1. Right. So the answer is that we can get everything except for y equals 1. So the image is, again, all of r excluding minus 1. Okay. That's about it. That's about it for this section, actually. Yeah, so
Slash.
R excluding. So it's excluding.
Just so that.
Yeah. So everything except for this negative one.